The East Antarctic ice sheet is the largest single mass of ice on Earth. It covers an area slightly larger than the contiguous United States. At its thickest points, it is nearly 5 kilometers deep. At the point where Vostok Station stands, a Russian research base in the middle of the continent, approximately 1,300 kilometers from the geographic South Pole, the ice is 3,769 meters thick. Beneath that ice, there is a lake. The lake is 250 kilometers long and 50 kilometers wide at its widest point. It covers an area of approximately 12,500 square kilometers. At its deepest point in the southern basin, the water is 800 meters deep. By volume, it is the 6th largest lake in the world, larger than Lake Baikal by area of surface ice coverage, comparable in volume to Lake Ontario. It is the largest subglacial lake ever discovered. The lake has not seen sunlight since the Miocene epoch. Geological analysis places the moment when glaciers sealed it at approximately 15 to 25 million years ago. At that time, the lake was an ordinary open-air body of freshwater, not unlike the lakes that exist on the surface today. The glacier advanced. The ice sealed it from above. The light stopped. The water did not freeze. Between 1990 and 2012, a team of Russian scientists drilled downward through the ice above the lake, meter by meter, through 3,769 meters of ancient glacial ice. On the 5th of February, 2012, at 8:25 in the evening Moscow time, the drill contacted the lake's surface for the first time. The water froze almost immediately, sealing the borehole from below. The drill was withdrawn. The lake has never been directly sampled. Vostok Station was established by the Soviet Union on the 16th of December, 1957, during the International Geophysical Year. It was not a comfortable posting. The station sits at an elevation of 3,488 meters above sea level on the East Antarctic Plateau. The air is thin. The terrain is flat in every direction, without landmarks, without variation. During the Antarctic winter, April through October, the sun does not appear above the horizon for months. The temperature drops below -60 degrees Celsius as a matter of routine. On the 21st of July, 1983, the temperature at Vostok reached -89.2 degrees Celsius, the lowest air temperature ever reliably measured on the surface of the Earth. The station's original purpose was not the lake. The lake was not yet known. The Soviets chose Vostok for a different reason: the ice. The East Antarctic ice sheet accumulates its layers over hundreds of thousands of years. Each year's snowfall compresses into a stratum. The stratum traps samples of whatever was in the atmosphere at the time: air bubbles, dust, volcanic ash. The deeper you drill, the older the layer. A drill through the full thickness of the ice sheet is, in effect, a time machine for the planet's climate. A core sample that reads like a continuous archive of atmospheric conditions going back hundreds of millennia. The Soviet drilling program at Vostok, later joined by French and American scientists, produced the most complete climate archive ever recovered from the ice. In 1998, after decades of work, a joint team reached a depth of 3,623 meters. The core they extracted documented 420,000 years of Earth's climate. 4 complete glacial interglacial cycles, the rise and fall of ice ages, the correlation between temperature and atmospheric carbon dioxide and methane across deep time. It was one of the most significant scientific data sets of the 20th century. The drill stopped at 3,623 meters. Not because the work was done. The drill stopped because the scientists had reached a boundary. Below them, approximately 100 meters further down, was the surface of the lake. The question was what to do about it. The lake itself had been suspected for decades before it was confirmed. In 1959, the Soviet geographer Andrei Kapitsa conducted seismic soundings to measure the thickness of the ice above the station. The acoustic reflections were anomalous, too clean, too uniform to come from rock or sediment. Kapitsa suspected a body of liquid water. He did not publish. The finding remained a working note. In 1974, a British team performing airborne radar surveys over the region detected a flat, reflective surface far below the ice, consistent with a lake. In 1993, J.K. Ridley, using altimetry data from the European ERS-1 satellite, confirmed what the surface shape of the ice implied. The glacier above the lake was unusually flat, distributed evenly, the way ice distributes itself over a liquid surface rather than over rock. On the 20th of June 1996, Kapitsa, Ridley, and their colleagues published their findings in Nature. The paper was titled "A Large, Deep Freshwater Lake Beneath the Ice of Central East Antarctica." 37 years after Kapitsa's first seismic sounding, the lake had a name. The decision to drill further, beyond the climate archive toward the lake itself, was not straightforward. The scientific case for doing so was clear. The lake had been sealed for between 15 and 25 million years. In that time, whatever biological or chemical processes had operated within it had done so in complete isolation from the surface world. The organisms that might have survived, if any had, would have adapted over geological timescales to conditions of total darkness, extreme pressure, sub-zero temperatures, and chemical energy sources unavailable at the surface. They would represent a window onto a form of life that the surface biosphere could not produce. The scientific case against was equally clear. Any drilling system capable of reaching the lake was, by definition, a system that had come from the surface. The drill itself, the borehole fluid, the equipment, all of it had passed through an environment populated by surface organisms. Introducing that material into a lake sealed for 25 million years would contaminate it irreversibly. You would not be discovering what lived there. You would be asking what you had brought. The borehole was not empty. To prevent it from collapsing and freezing over during the years of drilling, it had been filled with approximately 60 tons of kerosene and freon, industrial hydrocarbons. These fluids were less dense than water. The Russian team's argument was that when the drill reached the lake, the pressure of the lake water would push the fluid upward. The hydrocarbons would never enter the lake. The physics would protect it. The international scientific community was not persuaded. The United States National Research Council took a formal position, assumed that life exists in Lake Vostok and that it requires strict protection. American and British scientists argued that cleaner technologies, hot water drilling systems that produced no chemical contamination, should be developed before the lake was approached. The debate ran through international Antarctic science committees, through peer-reviewed journals, through diplomatic channels between research programs. The Russians disagreed. The drilling continued, and intermittently, through funding shortfalls and equipment problems and Antarctic winters that made sustained work impossible. Through the 1990s and into the 2000s, the final phase began on the 2nd of January 2012. The team was working against the Antarctic season. Summer operations at Vostok end in February, when the window for aircraft access closes and the temperature begins to drop toward its winter floor. By the 13th of January, the borehole had reached 3,738.5 meters, a technical problem with the drill cable suspended work. The team repaired the equipment and resumed. On the 4th of February, at a depth of 3,766.3 meters, the first contact with water was detected. On the 5th of February 2012, at 22:25 Moscow time, the drill of the 57th Russian Antarctic expedition penetrated the surface of Lake Vostok at a depth of 3,769.3 meters. What happened next was not what had been calculated. The lake water, under approximately 345 bar of pressure, the weight of nearly 4 kilometers of ice, shot upward through the borehole. The team had predicted the water would rise 30 to 40 meters. It rose 592.6 meters. A hydraulic fracture in the borehole wall had diverted drilling fluid, creating a channel that allowed the lake water to ascend far beyond the predicted level. The rising water mixed with the kerosene and freon in the upper borehole as it passed through. Within minutes, the mixture of lake water and drilling fluid began to freeze in the sub-zero temperatures of the borehole wall. A plug of ice formed at 3,768 meters. The drill was withdrawn. The borehole sealed from below. The 57th expedition had reached Lake Vostok. They had not been able to remain. The sample that existed was not what anyone had hoped for. The plug of ice at 3,768 meters contained lake water, the first actual lake water ever recovered from Vostok, but it was mixed with approximately 60 tons worth of drilling fluid that had occupied the borehole above it. The proportions were unknown. The degree of contamination was unknown. Before 2012, the biological analyses had used a different sample type, accreted ice. As the glacier moves slowly over the lake, it drifts at approximately 3 to 4 meters per year. Water at the lake's surface freezes onto the underside of the glacier. That frozen layer, the accreted ice, contains material from the lake itself, trapped in the moment of freezing. It is indirect, it is old, but it was the only sample available. In 2013, Sergei Bulat of the Petersburg Nuclear Physics Institute published the first analysis of the 2012 frozen lake water combined with accreted ice samples. He and his team identified 3,507 unique genetic sequences. 94% corresponded to known bacteria, 6% to known eukaryotes. Most of the identifications were consistent with organisms found in surface environments. Freshwater bacteria, soil organisms, species associated with drilling equipment. The pattern was consistent with contamination. Then there was one result that was not. A single bacterial phylotype, a genetic sequence representing one organism, shared less than 86% DNA similarity with any known species in the available databases. Standard bacterial species definitions require at least 97% similarity. 86% is not close. Bulat was careful. He did not claim a new species. He reported the finding and noted what it might mean. An organism that had evolved in sufficient isolation from known life that its genetic record had diverged to a degree that placed it outside the catalog of anything previously described. The response from the scientific community was immediate and split. Malin Kennicott II at Texas A&M University noted that the sample's integrity was inherently compromised. Accreted ice and borehole water had been questioned as reliable sample types precisely because the process of drilling and retrieval introduced surface organisms at every stage. David Pierce at the University of Northumbria said the finding was consistent with contamination and inconsistent with an extraordinary claim about new life. The phylotype was interesting. It was not confirmed. Bulat returned to the result years later using a more sensitive technique. Oxford nanopore sequencing, which can identify genetic material at very low concentrations with greater precision. The conclusion was different from the first. The unknown phylotype was also detected in control experiments, samples that had not been exposed to lake water at all. It was a contaminant. What had looked like a record of isolated life was, most probably, a signature of the drilling process itself. The lake, as far as the published science currently stands, has not yielded confirmed evidence of life. But what the science also cannot say is that there is no life. The evidence for absence requires a clean sample from the lake itself. That sample does not exist. What the analyses have produced consistently across multiple studies on the accreted ice is a biological signal consistent with an active ecosystem. Sequences linked to chemolitho-autotrophic bacteria, organisms that derive energy from chemical reactions rather than sunlight. Sequences associated with deep-sea hydrothermal vent environments. Thermophilic species whose presence is consistent with geothermal activity at the lakebed. A 2013 study in PLOS1 by Yuri Bulat's group identified sequences similar to marine bacteria, a marine hydrothermal vent fungus, and marine invertebrates. If those sequences are real, if they are from the lake rather than the surface, they imply a complete functioning ecosystem in the dark, operating on chemical energy for millions of years. That is exactly what NASA and the European Space Agency have been trying to understand for a different reason. Europa, the fourth moon of Jupiter, has a liquid ocean beneath a shell of ice estimated at 15 to 25 kilometers thick. Voyager 1 first photographed it in 1979. The Galileo spacecraft confirmed the ocean's existence by detecting a magnetic field consistent with a conducting fluid below the surface. The ocean is estimated to be 60 to 150 kilometers deep, larger by volume than all of Earth's surface oceans combined. The ice above it receives no direct sunlight at the surface, adequate for photosynthesis. The heat source is tidal flexing from Jupiter's gravitational pull. Enceladus, a moon of Saturn, has a smaller but more accessible ocean. In 2005, the Cassini spacecraft detected plumes of water vapor and organic material being ejected from fractures at the moon's south pole. Material from the subsurface ocean venting into space. Cassini flew through the plumes and analyzed their composition: water, salts, organic compounds, and molecular hydrogen. A signature of hydrothermal reactions between rock and water at the ocean floor. Both environments are analogous to Lake Vostok. The same conditions: liquid water, no sunlight, chemical energy, extreme isolation. The question of whether Lake Vostok contains life is, in part, a proxy for the question of whether Europa and Enceladus contain life. If life can survive for 25 million years in an isolated subglacial lake on Earth, the probability that it exists in the subsurface oceans of the outer solar system increases substantially. The lake is a calibration point for a much larger question. The ice core above the lake answered a different question with extraordinary precision. The 3,623-meter archive from Vostok, published in Nature in 1999 by a team led by Jean-Robert Petit, documented 4 complete glacial interglacial cycles going back 420,000 years. Temperature, atmospheric CO2, methane, and dust in a single continuous record. The correlation between temperature and greenhouse gases was direct and unambiguous. The current atmospheric concentrations of carbon dioxide, above 400 parts per million, are without precedent in the entire 420,000-year record. The ice said so with certainty. The lake said nothing because it has not been asked directly. The samples from the drilling program, the accreted ice, the frozen borehole water from 2012, are distributed across 3 research institutions: the Arctic and Antarctic Research Institute in St. Petersburg, the National Science Foundation's repository in the United States, and laboratories in France. scientists continue to apply new analytical techniques to the available material. The Oxford nanopore results revised Boulat's earlier finding. Future techniques will revise the current findings. The path to a direct sample requires a drilling system that introduces no biological or chemical material from the surface into the lake. Effectively, a sterile probe capable of operating at 3,769 meters depth. The technology is feasible in principle. It is analogous to what would be needed to sample Europa or Enceladus. It has not been built for Vostok. The engineering, the logistics, and the international agreement to proceed have not converged. The lake waits. During the Antarctic winter, Vostok Station operates with a reduced crew of approximately 13 people. There are no flights in or out. The runway cannot be used below approximately minus 50 degrees Celsius. In the depths of winter, the temperature drops below minus 65 regularly. The crew maintains the instruments, monitors the station's systems, and waits for the summer season to return. They are, for 6 months of the year, the most isolated people on Earth. Below them, 3,769 meters below, straight down through the ice, the lake is as it has always been. The water is at approximately minus 3 degrees Celsius. It is liquid only because the pressure of the ice above prevents it from freezing, the same pressure that has held it in this state for millions of years. It is completely dark. If the estimates of geothermal activity are correct, vents at the lakebed are producing heat and chemical energy, as they may have done throughout the isolation period. The drill is still in the borehole, held in place by the frozen plug at 3,768 meters. The samples are in laboratories on 3 continents. Scientists are working with them. The biological question, whether anything lives in that lake, whether anything has persisted through 25 million years of darkness and pressure, remains open. The data available is not sufficient to answer it. The lake is 250 kilometers long, 50 kilometers wide, 800 meters deep in the south. It has been sealed since the Miocene. It has been drilled to its surface, but not into it. It has been sampled at its margin, but not at its interior. The question of what it contains is filed. The lake, after 25 million years, is not in a hurry.